Hello folks, welcome back to Precalculus. Today we're in chapter 2, section 7. We're going to be talking about piecewise functions. Okay, so a piecewise function is any function defined by two or more equations in which each equation or piece has a specified domain. Okay, a specified domain. So here you see an example of a piecewise function. So what this means is this function f is going to look like 6x plus 2. It's going to look like this line when x is between 3 and 8. Okay, and it's going to look like this line right here, this parabola, when x is bigger than 8. Okay, so that's how you look at a piecewise function. All right, these are the functions, and those are the domains. Okay, so let's take a look right here. Right here, clearly we see a piecewise function. All right, it is not a function like we talked about in previous sections. This is not a normal shape of a graph, so we're going to have to use a piecewise function to construct this graph. Okay, so let's go ahead and make our function f of x. And I see it's going to be two pieces. I see a straight line here and then a slanted line here. Okay, so let's take a look at this straight line first. It looks to me like it's about at y equals 7. Okay, so my function is going to be y equals, or f of x equals, same thing, 7. And the domain is going to go from right here to right here. The domain, the x-coordinate, is going to go from right here to right here. So it's going to be from -9 all the way to 1. All right, so now let's take a look at this second piece of the puzzle here. The second piece of the piecewise function is this negatively sloped line. Well, first of all, we know it's going to be some kind of y equals mx plus b. So we know what the equation should look like. Okay, and let's find the slope here. So the slope looks like it goes over 1, down 1 in each direction. So we know the slope is going to be -1. We can make a little note of that. The slope is going to be -1. For just this little piece. We're just talking about this piece right here. Okay, now let's go ahead and find the y-intercept. We've got the m, we need the b. Okay, now it doesn't have a y-intercept, but I can see that like they kept going, it would have a y-intercept right here. That's where it would be. So the y-intercept would be 8. Okay, so the equation of my line is going to be -x plus 8. Now we need to find out what the domain is. Now we want the domain to just be from that red line to here. So you can see if I make my vertical boundary lines, my domain is going to be somewhere between 1 and 11. And there's your piecewise function. The piecewise function is y equals 7, a horizontal line, between -9 and 1. And it's this sloped line, -x plus 8, between 1 and 11. And you can see that both of them meet right here when x is 1. That's why we have equal to 1. Okay, so let's move on now into graphing a piecewise function. So graphing piecewise functions from the function here. Okay, so first of all, let's fill in some blanks here. So you have a couple ways that you can do graphing. You can use a t-table, okay, using values in the specified domain. So plugging in x values within the domain that they give you, okay, and you can plot those points. That's a fine strategy as long as you know the shape of the graph. Okay, you do need to know your parent functions. So now is a great time to pause the video, take out your previous sections that have your parent functions on there so you do know the shapes of your graph. That's going to be extremely important. Okay, or you can graph each piece in its entirety using the basic transformations from the parent functions, and then erase portions outside the specified domain. Okay, so those are two different ways that you can do it. I'm actually going to do our first example in a hybrid of that. I'm going to show you this way and I'll show you the second way. You can choose what's best for you. Okay, but let's talk a little bit about what a continuous function is. A continuous function, you can draw the entire graph without lifting your pencil. So it is smooth. It is a smooth curve. Okay, it can be drawn without lifting your pencil. A discontinuous function, the entire graph cannot be drawn without lifting your pencil. Okay, so sometimes you have a break, or you have what we call pointwise discontinuity, a hole in the graph. Okay, and we'll talk a little bit about that coming up. Okay, so let's take a look here at this first example. Now, you notice I am going to use pencil here because I'm going to start drawing and then I'm going to erase. So the first part of the piecewise function is y equals -4. Y equals -4. So I'm going to show you using the second way here, where I'm going to graph the whole thing and then I'm going to erase anything outside of the domain of x less than -2. So if y is equal to -4, y equal to -4 is a horizontal line. I'm try to draw it really dark for you guys. Right there. Okay, so there's our y equals -4. Now we only want it when x is less than -2. So basically I don't want anything from here to the right. Okay, so I'm going to erase everything to the right of -2. I don't need any of that stuff. And because it's less than -2, I'm going to use an open dot for now. Okay, so there's my piece. There's y equals -4 when x is less than -2. So now I'm going to use the first way. Okay, I know the shape of an absolute value graph is going to be V-shaped. Okay, it's going to be V-shaped. And this negative outside is going to make it upside down, and then it's going to slide down too. So I'm essentially going to have something like that. Okay, that's why it's super important to pull out those parent functions and have them visible to you right now so you don't forget what each graph looks like. Okay, so if I make a little t-table, it's a little xy table for my absolute value, and I say, okay, I need to plug in values between -2 and 4. I'm going to plug in -2. Let's see what I get when I plug in -2. So the absolute value of -2 is 2. This negative is going to make it -2 again. -2 is going to be -4. So that's actually this point where I have an open dot. Now it becomes a closed dot. Okay, now let's plug in 4. Okay, let's plug in 4. So the absolute value of 4 is 4. This is going to make it -4. -2 is going to make it -6. So when I plug in 4, I'm going to get out -6. And I have an open dot right there because it's less than 4. All right, now I do know that I should have a vertex of some kind. Okay, and it should be somewhere in the middle, but in between these points. But what I do know is, let's take a look back at this transformation. My normal absolute value graph has a vertex at the origin. This negative sign flips it upside down, which we can see is about to happen. And this -2 slides it down 2. So I know that my vertex is down 2. And I know my graph is going to look like this. I'm going to make it dark for you guys. It's a little bit too thick. I don't like it. There you go. You can see that we have an upside down absolute value graph slid down 2. Okay, so now let's do one more. I'm going to do it using the t-table as well. Okay, so this graph right here, the square root graph, is going to look like a little arc. Okay, this 3 in front of it's going to be a vertical stretch by 3, so it's going to climb a little bit faster. And it's going to be shifted down 9. Okay, so just knowing that it's going to be shifted down 9. And I'm only going to plug in values greater than or equal to 4. Well, 4 happens to be a perfect square. So that's perfect. I can do that in my head. Okay, so let's plug in 4. The square root of 4 is 2. times 3 is 6, minus 9 is negative 3. So the point 4, negative 3, is on our graph. And I'm going to use a closed dot because it says greater than or equal to 0. Okay, so now I know that my graph is going to look like this shape. It's going to look like this. It's got a vertical stretch of 3. It's been shifted down 9. Okay, that's no big deal. But essentially, I know it's going to be this shape. So I just need one more point, and I can make that shape. Okay, so let's plug in another perfect square. I'm going to go ahead and plug in 9. Let's see what happens when I plug in 9. So the square root of 9 is 3. Times 3 is 9. Minus 9 is 0. So the point 9, 0 exists on our graph. So 2, 3, 4, 5, 6, 7, 8, 9. And now I can draw my square root graph. And I'm finished. Okay, I have y equals negative 4 over a specified domain, x is less than negative 2. I've got my negative absolute value of x minus 2 between negative 2 and 4. And I've got my 3 square root of x minus 9 for any x that's greater than 4, or greater than or equal to 4. So what I want you guys to do right now is go ahead and stop the video, pause the video, whatever you want to do, and you're going to do all 3 of the functions on the back, all 3 piecewise functions on the back on your own. Okay, they do need to be completed for class. I strongly suggest that you get out your parent functions so you don't forget what each shape of these squareds and cubes, and here we got more squareds and cube roots and all these things, so that you don't forget what shape to use. So you can use either the erase strategy or the plot and t-table strategy, whatever works best for you. But we'll talk about these in class, and I can answer your questions. I look forward to helping you.